Welcome to my workshop. I'm Jim. Today I want to share with you the procedure for making a metal box called an enclosure for the high voltage power supply I built in a previous tutorial using the transformer from a microwave oven. This is a picture of the enclosure before I started to mount the components. The aluminum sheet is 0.04 inches thick. That's 1/25th of an inch. This thickness is a good balance between rigidity and workability for making an enclosure. We'll need a full-size pattern for cutting and drilling. I found it convenient to draw the pattern using the same software I use to lay out printed circuit boards. This is the completed drawing for the power supply's enclosure, prepared using Express 123. If this was a printed circuit board, the yellow lines would be the silkscreen layer. Everything is on this one drawing, including notes I made to myself as reminders. In places, I've shown the projection of a component or a board from one face onto another. I've done this to ensure that there's adequate clearance where it's needed, and to prevent physical conflicts. Where holes are to be drilled, I've placed a PCB pin to mark the center. This is the on-off toggle switch, with the body of the switch shown in outline. The printed circuit board software will be able to export either a mechanical drawing or an image of the silkscreen layer. Express 123 can do both, but I prefer to use the latter. It copies the silkscreen layer onto the clipboard, from which it can be pasted anywhere else. I place the image on the clipboard into a blank Word document. At 1:1 scale, the pattern is a lot larger than a standard 8.5 by 11 inch piece of paper. That's not a problem. The cropping and scaling features in Word permit various parts of the drawing to be printed onto separate pieces of paper. I then cut and paste, and I'm talking about real scissors and real paste, the individual pieces of paper to make full-size drawings. I use a glue stick, not a pot of paste. You don't want too much moisture in the glue. Damp paper stretches easily and can ruin the scale. A glue stick is just about right. The power supply enclosure uses 4 separate patterns. There's one for the sheet aluminum cover and another for the sheet aluminum base. The guidelines for cutting are a little bit too thin to see clearly in this photograph. The pattern for the base is 22 inches long. In addition to the 2 patterns for the metal enclosure, there are 2 patterns for pieces which I'll cut out from non-perforated vector board. One is a mount for the transformer, which will keep it isolated from the metal box. The other is a small board which will be mounted onto the front panel and which will hold bolts to which the high voltage leads can be secured, so that they, too, do not touch the metal box. Incidentally, what I'm calling non-perforated vector board is simply printed circuit board without any copper. I think that vector board was a trade name used in the early days of printed circuit boards. These are the patterns and the aluminum sheet from which they'll be cut. All residue should be removed from the aluminum using acetone or Goo-Gone. These are the other 2 patterns and the vector board from which they'll be cut. The next step is to glue the patterns onto the aluminum sheet and the vector board. This is the aluminum sheet. There's a trick to gluing paper onto aluminum. First, apply a layer of glue to the raw aluminum and let it dry. Then apply the glue to the back of the paper and press it into place. Pre-gluing the aluminum helps. I've found that the bond is better. There's also a second trick. Glue some scrap paper onto the back of the aluminum sheet. The side with the pattern is going to be the inside of the enclosure. That means that the side without the pattern is going to be the outside, the side that you'll see, the good side. A layer of paper on the good side will minimize scuff marks and scratches, which are inevitable when the sheet is being cut and drilled. This is the vector board with its 2 patterns glued in place. Vector board holds glue a lot better than aluminum, so there's no need to pre-glue the vector board. As a final step before cutting, run some Scotch tape down all of the edges which will be cut. This helps the pattern from tearing up as the blade goes by. Tape with a matte finish is better than glossy tape, but use what you've got. The best way to cut vector board is using a hacksaw. The edges can be smoothed and the corners rounded using a sanding block. These are the transformer mounting board and the keeper board after cutting and sanding. The best way to cut aluminum sheet is using a jigsaw. It's helpful to use some wooden bars or planks to clamp the aluminum sheet down while cutting. Actually, it's easier to cut vector board when it's clamped too. This jigsaw blade has 24 teeth per inch. It's 3/8 of an inch wide, so that it holds a straight line quite nicely. If the jigsaw was previously mounted on a table, be sure to reattach the plastic shoe. The shoe will keep the jigsaw's metal bottom from digging into the pattern as you saw. Use a metal file to smooth the edges of the aluminum sheet and round the corners. This job will be a lot easier if you make a temporary vise on the edge of your workbench, using some scrap wood and a few clamps. This 1x4-inch plank is secured to the edge of the workbench by these two clamps. A wooden bar is secured to the front face of the plank by these two clamps. A metal edge to be filed should just peek up above the crack between the two pieces of wood. A fine metal file should make short work of any rough spots. A square or triangular file might help with the interior right angles. This is the power supply's base, now cut out and filed and ready for holes to be drilled. And now for drilling. Drill pilot holes first for every hole. A 1/16-inch bit is perfect. Resist the temptation to drill out any of the holes to their finished sizes, even if you have the bolts ready at hand. The best Dremel accessory I've ever used is this flexible shaft. I bought this shaft more than 15 years ago and haven't done a single bit of maintenance. There's no lubricant or anything like that. The end piece is almost as small as a pencil and allows for very precise positioning. It's much better than a drill press. The best tool to use for marking hole positions on the aluminum sheet is this snap punch. As one presses down on the case, a spring inside is armed. It releases with a snap and punches a small indent into the surface. The 1/16-inch bit on the Dremel tool will quickly zero in onto the indent and drill a pilot hole right where it should be. Marking hole positions only needs to be done on the aluminum sheet. Vector board is soft enough that pre-punching indents is not necessary. This is the noise reduction circuit taken directly from the microwave oven. It was built on its own little printed circuit board, which makes it handy to mount on the inside of the back panel of the power supply. 2 number 6 bolts hold it in place, and I've used 2 nylon spacers to keep it from touching the metal enclosure. This is the high-voltage transformer bolted to its mounting board. It's secured using 3 number 6 bolts and this number 10 bolt. Remember that one of the high-voltage leads of this transformer is connected to the frame. All ground wires in the power supply will be attached to this number 10 bolt. The 2 capacitors will be held in place using cable ties, which pass through 2 holes drilled in the mounting board. This is the transformer mounting board once again, but with the transformer removed. This is the number 10 bolt that I described earlier. Here, the transformer mounting board is secured to the power supply base. You can see that I've used nylon spacers again. They keep the bolts which actually touch the transformer's frame away from the sheet metal enclosure. As I turn over the base, you can see that I used the mounting bolts for the mounting board to secure the rubber feet in place. This is the keeper board. It will be mounted on the front side of the front panel of the power supply. Its sole purpose is to provide an insulated base for these 3 bolts. These bolts have no structural function. The high-voltage leads which come out of the power supply can be temporarily secured here. I've added wing nuts to make them a little more convenient to use. The front panel, therefore, must have 3 large holes to provide spacing around the heads of the keeper bolts. I've already cut out one of the holes. I'm lucky. I have a 1-inch diameter punch to do the job. It works like this. There's a cutting cylinder which slides into a hollow base. This bolt passes through the base, the workpiece, and the cutting cylinder is threaded on. When the bolt is turned, the cutting cylinder is drawn through the aluminum sheet up into the hollow base. The sheet is reinforced by the lips on this hollow cylinder. This ball bearing race makes it easier to turn the bolt against the friction. The hole which results may have a very small lip on the inside, so it's useful to set things up so that the cutting cylinder starts on what will be the outside and punches through, leaving the lip on the inside. If you don't have a punch, then the best thing to do is to drill a medium-sized hole, say a 1/2 inch diameter hole, and then to use a round file to enlarge it to a satisfactory size. My advice is to avoid using a large drill bit, such as a 3/4 inch drill bit or a 1-inch drill bit. A large diameter drill bit can easily tear into the aluminum sheet. Even with a drill press and using a lot of care, it only takes an instant for one of the flanges of the bit to bite in to the aluminum and leave a warped mess. This is the base of the enclosure with all of the holes drilled and chamfered. It's time to start bending. There are 12 tabs around the perimeter of the base. They're all going to be bent up at right angles to the base. The cover of the enclosure will lie flat against the 12 tabs. This is a detail of 2 of the tabs. Note that there aren't any holes in the tabs, not even pilot holes. These tabs will be bent along the lines of the arrows. That will leave a gap between the cover and the base. The gap will allow passive air cooling of the transformer inside. The tabs are not very big, so an easy way to bend them is using a vise. Position the sheet in the vise so that the bend line is exactly coincident with the top edge of the front jaw. The sheet is going to be pulled down in this direction. Then clamp a piece of metal or hardwood onto the back. This happens to be a slab of aluminum a 1/2 inch thick. It will keep the sheet flat as it's bent down. Put as much force as you can along the jaw of the vise when you bend the sheet. If you have a brake, go ahead and use it, although it's a bit of overkill for these little tabs. This red line is the hinge line. When the handles of the brake are pulled up, the front plate will rotate up around the hinge line. These are the chisels. The sheet is sandwiched between the plate and the chisels and will bend when the front plate rotates up. This particular brake can be adjusted. The distance between the tip of the chisels, which is highlighted by the yellow line, and the hinge line can be adjusted. This is a close-up view of the area around the tip of the chisels. The red line is the hinge line. The yellow line is the tip of the chisels. I've adjusted the brake so that the hinge line is offset by 1/25 of an inch from the front of the tip. That's the thickness of the aluminum sheet. Position the sheet so that the center of the bend is coincident with the tip, not with the hinge line. The pencil line on the yellow piece of paper is where the center of the bend will be. I designed this enclosure a little differently than most. This is a partial front view of the power supply. The front face is shaded in purple. The cover is seen in cross-section and is shaded in blue. I want there to be a gap of 3/16 of an inch or so between the front face and the cover. I drew the cutting pattern with 12 tabs, 2 of which are shown in this view. Let me move the cover slightly to one side to show the tabs in full as they appear on the pattern. I'm going to shade one of the tabs in red to make it clearer in the next view. Before bending, of course, the tabs and the front face lie in the same plane. This is a partial end view of the brake with the sheet in position and ready for bending. The tip of the chisels lies at the junction between the red tab and the purple face. The front plate of the brake supports the front face of the enclosure. The hinge line is slightly offset towards the front of the tip of the chisels. When the brake's front plate is pulled up, it will rotate up by 90 degrees and fold the metal sheet. The metal will deform at the bend. Generally speaking, there will be more stretching on the outside of the bend than there will be compression on the inside. As a first approximation, you can assume that the interior dimensions will be preserved. This means that the bent metal will be slightly oversized by the thickness of the sheet. After the tabs have been bent, the front view will look like this. When the cover is moved back into contact with the tabs, it will be slightly further away from the face by the thickness of the sheet than the line is drawn on the pattern. As we will see, this will not be a problem. There's no need to adjust for the radius of the bend. This is the base of the power supply before the tabs on one side are bent. After it's been bent up by 90 degrees, the base looks like this. This is the base of the power supply after all 12 tabs have been bent. The next step is to fold the front and back panels up so the base has the shape of the letter U. I've placed a metal backing plate beneath the piece with its edge along the line of the proposed bend. I've clamped another slab of metal on top with its edge coincident with the line of the bend. Lastly, I've clamped a third slab underneath and pressed it butt to butt as tightly as possible against the edge of the first slab. As you pull up on the end of the overhang, put as much force as you can on the bottom of the assembly in the neighborhood of the yellow bend line. I used the brake to make these last two bends in the base. This is the setup before bending the rear panel. The tip of the chisels has been lined up at the line drawn on the pattern. After the bend has been made, the base is flipped around and made ready for bending the front panel. Once the tip of the chisels has been lined up at the line drawn on the pattern, the front panel can be bent up. That's the last bend to be made in the base. This is the base after the last bend. The cover will lie on top like this. The two sides are going to be bent down to make an upside-down letter U. Remember that the pattern was glued onto the side of the cover that will be inside the metal box. So we're looking here at the side that does not have the pattern. Before making the two bends in the cover, we need to verify the locations of the bend lines. Here I've placed the cover on the workbench with the inside, that's the side with the pattern, facing up. The yellow lines mark the bend lines on the pattern. I've then placed the power supply's base with one end. It doesn't matter whether it's the front panel or the rear panel facing the cover. What I'm interested in is the distance between the outside faces of two tabs on opposite sides. When I drew up the cutting patterns, the distance between the red arrows was exactly the same as the distance between the yellow lines. When the tabs were bent, though, some extra width was created. The result is that the distance between the red arrows will be slightly greater than the distance between the yellow lines. In this case, the extra distance is just under 1/16 of an inch. The width of the cover will be perfect if we add just under 1/32 of an inch to each side. I therefore drew new bend lines on the cover, slightly further apart than the ones on the original pattern. The locations of the new bend lines are shown in green. In the brake, the cover is positioned with the tip of the chisels on the newly drawn bend line. After bending one side up, the cover is repositioned for the other side. Bending it up completes all of the bending needed for this enclosure. The cover should slide down nicely over the base. We can now start preparing the holes for the attachment screws. Early on, I drilled 12 pilot holes around the perimeter of the cover. These pilot holes should now be pretty close to the centers of the folded over tabs of the base. Remember that I didn't drill any holes in the tabs. I'll do that now. The base and the cover will not have been bent perfectly square. There'll always be a bit of racking and twisting. I deal with the inevitable misalignment by drilling the attachment holes in 5 separate groups. I start with just the 2 holes along the top edge of the front panel. With the cover and base held firmly in the desired relative position, I use the Dremel tool and a 1/16 inch bit to drill through the pilot holes in the cover to create pilot holes in these 2 tabs. I use number 6x32 machine screws as fasteners. The holes in the cover will need to be enlarged so that these screws, which are actually bolts, can slide through freely. A bit with a diameter of 9/64ths of an inch is ideal. That's 1/64th of an inch larger than 1/8. The holes in the tabs must also be enlarged, but not so much. The best bit for them is 7/64th of an inch in diameter. That's 1/64th of an inch smaller than 1/8. The number 6 machine screw won't fit into this hole. It's not intended to. The hole is going to be tapped. The 6x32 tap threads the holes as it's turned. A tap has a tendency to stick when it's threaded through aluminum. That's because the aluminum is deformed as well as being cut. The deformed part tends to grab the tap. It's just as easy to break a tap in an aluminum hole as it is in a steel hole. Friction will be greatly reduced with a dab of oil. Once the holes have been enlarged and the inner ones tapped, the cover can be screwed to the top of the front panel. Then turn the unit around and process the 2 holes along the top edge of the rear panel. Note that these 2 tabs extend a little bit beyond the cover when the base is not being held in place. That's simply because the bends weren't quite 90 degrees. And this is the reason why I drill the attachment holes in separate groups. Hold the 2 pieces in the right relative position and drill the pilot holes through the tabs. Enlarge the holes and tap the inner ones. Note that it will be necessary to remove the screws along the top of the front face in order to do this. This is a good time to mark the inside of the cover. Note that the cover is symmetrical. The front end is nominally the same as the rear end. On the pattern, the 2 ends are identical, but we're now custom fitting the attachment screws, so there's going to be a very small difference between the ends. Avoid aggravation by turning the cover over and writing down which is the front end and which is the rear end. That will ensure that the cover is always replaced in the correct orientation so that the holes are perfectly aligned. Once the cover has been reattached with 4 machine screws on top, we can work on the sides. I find the best way to proceed is to do 1 hole at the bottom of each side. Once these 2 holes have been drilled and tapped, the cover will be secured with 6 machine screws and everything should be square and shipshape. Then the remaining 6 holes, 3 on each side, can be processed all at the same time. This is the completed enclosure. I've washed off all the paper and the glue using hot water and a sponge. I haven't reattached the cover to the base because the next step is to mount the components. The 1 bolt shown here marks the front end of the cover. Washing off the pattern also washed off the written note I'd made inside the cover earlier. As part of completion, I'll add a permanent label here. I don't use pop rivets. Well, I do use them, but not for enclosures which will hold electrical circuits. The problem is not that pop rivets can't be removed, because they can. Although it's a bit of bother, pop rivets can be drilled out if one needs to get back inside the enclosure. The problem is this little ball. The little ball is on the end of a plunger which passes through the hollow barrel of the rivet. The plunger is inserted into the pop rivet tool. When the handles of the tool are brought together, the plunger is pulled up inside the tool. The little ball pulls on the end of the barrel and deforms it. If the rivet passes through 2 pieces of sheet metal, they'll be pulled together. The plunger is pulled until it snaps. Now, where's the little ball? In this case, the little ball is still inside the barrel. This is an end view of the rivet, and the little ball can be seen inside. It's loose, and I can shake it from one end of the barrel to the other, but it's still trapped by the deformed metal. Sometimes, though, the little ball comes free and could rattle around inside the enclosure. A little metal blob has no place inside an enclosure with electrical circuits, whether they're high voltage or low voltage. I don't use sheet metal screws either. There are 3 different sizes of sheet metal screws shown on the right side, which can be compared to the 6x32 machine screws on the left. The sheet metal screws have very coarse threads. They're intended to catch the edges of a pilot hole easily and then to advance quickly when they're turned. Because their threads are so coarse, sheet metal screws only make 1 cut through the sheet metal. Actually, it's 2 cuts, one on either side of the pilot hole. A single sheet metal cut is satisfactory for steel sheet, but not for aluminum sheet. Aluminum is so soft that there's a risk that the pilot hole will be reamed out, especially if the screws need to be removed and then replaced. My preferred fastener is the number 6x32 machine screw. The number 6 refers to the diameter of the screw. The number 32 is the number of turns per inch. Since each turn advances the screw by 1/32 of an inch, there's room for 2 complete turns in a metal sheet which is 1/16 of an inch thick. That's quite a bit more contact surface than offered by a sheet metal screw. Unless over-tightened, machine screws can be removed and reused many times. I find that mounting the components onto a nice new shiny enclosure is one of the most satisfying parts of any electronics project. It's a particular joy when everything goes together smoothly and according to plan. I use a small label-making machine to make the labels. It produces an adhesive-backed strip with the desired wording. It has only limited graphics capability. Its chief advantage is that it's fast and convenient. Once upon a time, I tried silkscreening. Whatever I was doing did not lead to success. The images were much too crude for my purpose. Most of the time, the result was just a gooey mess. I've also tried Pulsar's toner transfer system. Their system works perfectly for making printed circuit boards. It's the only technique I use for that, but I could not get their procedure for making decals to work for me. After all the parts have been mounted and wired up, the circuit will have to be tested. Then, at last, the cover can be screwed in place. And this brings us to the final part of any project, putting the tools away. It's here that Murphy's other law applies. The way he put it, no matter how big your workshop is, it's 20% too small. There was a time long ago when a project I was working on needed a small bending brake. Why get a small one, I asked myself, when a big one can do this job and a whole lot more in future? Now I know. A big brake takes up a lot of space. You can't just tuck it away in a corner of your workshop or hang it up on the wall. A better choice would have been a smaller brake, perhaps with a 24-inch or 30-inch width. Be warned. Well, that's all for today. Thanks for watching. See you next time.